The ground you stand on contains atoms from a star that died long before Earth was born. This is the universe recycling itself, a continuous cycle where stardust is endlessly transformed. By the end of this journey, you will understand the spectacular life and death of stars and see your own profound connection to the cosmos. We will uncover how a star's violent end seeds the galaxy with the ingredients for new worlds and even life itself. How does the death of a star in a faraway galaxy billions of years ago lead to the air in your lungs today? What does it mean to be made of stardust? How does this grand cycle reflect on our own place in the universe? Deep within the cold, silent darkness of space, immense clouds of gas and dust drift like cosmic ghosts. These are nebulae, the stellar nurseries where the story of a star begins. They are not empty voids but rich reservoirs of primordial material, the very ashes left behind by long-dead stars. In places like the magnificent Orion Nebula, gravity acts as an invisible sculptor, patiently drawing these particles together over millions of years. What starts as a faint, cold knot slowly collapses under its own weight, spinning and heating up as it condenses. The pressure and temperature at its core climb to unimaginable heights until finally, a cosmic switch is flipped. Nuclear fusion ignites, a process where hydrogen atoms are forced together to create helium, unleashing a torrent of energy. In that brilliant flash, a new star blazes to life, pushing back the darkness of its nursery. The fate of this newborn star is sealed from this very moment. Was it born from a vast reservoir of matter, destined to become a colossal blue giant, burning fiercely and dying young? Or did it form from a more modest collection of gas, becoming a stable, long-lived star like our own sun? This initial mass is the star's destiny, writing the entire script of its life, its death, and the chemical legacy it will one day return to the cosmos. For now, the star enters its long, stable adulthood, known as the main sequence, where it will spend the vast majority of its life. This stable chapter, the main sequence, is a star's long and brilliant prime of life. Deep within its core, a titanic struggle rages continuously, yet from the outside, everything appears perfectly serene. The star's own immense gravity constantly tries to crush it inward, an unrelenting force of compression. But this force is met by an equally powerful outward push from the furnace at its heart, where nuclear fusion turns hydrogen into helium. These two opposing powers lock into a perfect standoff, a cosmic balancing act that can last for billions of years. For a star like our Sun, this period of sustained stability spans an almost unimaginable 10 billion years. It is this unwavering constancy that creates the conditions for planets to coalesce from the surrounding disk of dust and gas. It is this reliable, gentle flow of energy that, on at least one world, allowed the first delicate molecules to assemble and eventually blossom into life. The star is a masterful engine, patiently and methodically burning through its vast reservoir of hydrogen fuel, but this very process contains the seeds of its own end. With every second that passes, the star is subtly altering its own internal chemistry, transforming the lightweight hydrogen in its core into heavier, inert helium. It is writing the final chapter of its life with the very ash its fusion creates. This long, calm adulthood is not a permanent state, but a graceful, slow-motion countdown to an inevitable and dramatic transformation. But a star cannot burn forever. The first true turning point arrives not with a bang, but with a quiet, internal crisis. After billions of years of stable existence, a star like our Sun finally exhausts the hydrogen fuel in its core. The steady fusion process that defined its long adulthood sputters and stops. The delicate balance that held for so long is shattered. With the outward push of fusion gone, the star's immense gravity, patient and relentless, finally wins the battle. The core, now a dense ball of inert helium ash, has no defense. It begins to collapse inward under its own weight. As this core contracts, a remarkable thing happens. The crushing pressure heats the helium to incredible temperatures, far hotter than it ever was during the star's main sequence life. This fierce new heat does not immediately reignite the core. Instead, it superheats a thin, shell-like region of untouched hydrogen that still surrounds the helium center. In this shell, hydrogen fusion roars to life with a new and furious intensity. The energy unleashed by this shell fusion is immense, and it has a dramatic effect on the star's outer layers. A tremendous wave of pressure pushes outward, forcing the star's vast atmosphere to swell to a monstrous size. The star begins to inflate, expanding hundreds of times beyond its original diameter. As it grows, its surface cools, shifting its light from a familiar yellow-white to a deep, ominous red. The stable star we knew is gone. In its place is a red giant. Our own sun will one day undergo this very transformation, swelling so large that it will engulf the inner planets, its fiery edge stretching far into the solar system. This is the star's first and most visible rebellion against its fate, a spectacular prelude to the far more violent and creative final acts that are yet to come. This final bloom is a star's last great act of creation. As the red giant swells, its heart becomes a forge of immense power. With the core crushed and heated to incredible extremes, it finally reaches a temperature of over 100 million degrees. At this threshold, a new and more complex fusion process ignites. It is called the triple alpha process, where 3 helium nuclei are slammed together to form a single, stable nucleus of carbon. This is the moment the star begins building the very stuff of worlds. In some of the most massive red giants, this forging continues, with helium and carbon fusing to create oxygen. For the first time in its life, the star is producing elements far heavier than the hydrogen and helium it was born from. It is manufacturing the fundamental ingredients for future rocky planets, and indeed for life as we know it. Yet this creative burst comes at a terrible cost. The star becomes profoundly unstable, its outer layers churning like a boiling ocean. Powerful stellar winds, far stronger than the solar wind our sun emits today, begin to blow these newly enriched layers into the void. The star is literally tearing itself apart, shedding its own skin back into space. This is the first direct act of cosmic return, a slow-motion explosion that seeds the surrounding interstellar medium with carbon, oxygen, and other vital elements. It is a beautiful and destructive paradox. While the star's immense, cool atmosphere may engulf and vaporize any inner planets that once orbited it, it is simultaneously flooding the galaxy with the very materials needed to build new worlds and perhaps new life. But this prolific phase cannot last. The star is burning its remaining fuel with a desperate intensity. What happens when this last reservoir of helium-2 is finally exhausted, and the star's core is left with nothing but inert carbon and oxygen ash? The final and most dramatic chapter of its life is about to begin. That quiet, crushing collapse of the core does not last. Inside a star like our future sun, a truly spectacular and hidden detonation is about to occur. The core, now a dense ball of helium ash, is squeezed by gravity to incredible densities and heated past 100 million Kelvin. At this extreme threshold, the helium itself becomes the fuel. But its ignition is not a gentle flicker, it is a cosmic bomb. In a runaway chain reaction lasting mere minutes, helium nuclei are slammed together in a frantic rush to form carbon. This is the Helium Flash, a violent thermal nuclear explosion that unleashes more energy than our entire galaxy of stars for that brief, brilliant moment. Yet from the outside, the star appears unchanged. The flash is completely contained within the star's incredibly dense core, its energy absorbed in the frantic work of pushing back against gravity's crush. This internal explosion fundamentally changes the star. When the flash subsides, the star finds a new, temporary peace. It settles into a stable phase where helium fuses calmly into carbon in its core, while a shell of hydrogen continues to burn around it. This period of dual shell burning is brief in cosmic terms, but it is one of the most important creative phases in the universe. It is the primary way that carbon, the fundamental building block of life as we know it, is forged and released into the cosmos. Inside the star, a complex layered structure emerges like a cosmic onion. At the center, a core of carbon and oxygen grows. Surrounding it is a shell where helium fuses into carbon. Around that, a separate shell where hydrogen fuses into helium. Each layer is a testament to the star's history, a record of the fuels it has consumed in its long war against collapse. This intricate elemental factory is the star's final, stable configuration, but the piece is fragile. The star's ultimate fate now hinges entirely on a single, simple question. How much mass remains in its core after this grand display of creation? The answer will send it down one of two profoundly different paths, one leading to a quiet, crystalline end, the other to one of the most violent explosions in the universe. The star's final, gentle rebellion begins when the last of its fuel is gone. With no more fusion to support it, the churning outer layers, now rich with newly forged carbon and oxygen, are cast off into the void. This is not a violent explosion, but a slow, elegant unfurling. The star sheds its atmosphere in a series of luminous pulses, creating a vast, incandescent cloud that expands into the darkness. Through early telescopes, these glowing shells appeared as small, greenish disks, reminiscent of distant planets like Uranus. This visual coincidence led to the name Planetary Nebula, a label that has stuck for centuries, even though these structures have nothing to do with planets. What we are witnessing is the star's soul laid bare. At the very center of this expanding glow, the star's core is exposed. No longer shielded by a massive atmosphere, this tiny, incredibly dense sphere of carbon and oxygen is blisteringly hot, shining with a fierce white light. It is a white dwarf, the Earth-sized ember of the giant star that once was. The intense ultraviolet radiation from this searing hot cinder floods outwards, striking the slowly expanding shell of ejected gas. This energy charges the atoms within the cloud, causing them to fluoresce in a spectacular display of color. The Ring Nebula and the Helix Nebula are two of the most famous examples of this final, artistic phase. Their intricate shapes, from perfect rings to what looks like a giant cosmic eye, are the star's last signature written across light years of space. But this beauty is more than just a farewell. The glowing gases are a cosmic delivery, a cloud of stardust now seeded with hydrogen, helium, carbon, oxygen, and nitrogen. These are the very elements that were forged in the star's heart during its red giant and helium flash phases. This gently expelled material is the star's ultimate contribution, a vital infusion of complex atoms into the galactic reservoir. It will mix with other interstellar clouds, becoming part of the raw material for a new generation of stars, for rocky planets, and for the chemistry of life itself. The star gives its body back to the universe, ensuring its components live on long after its light has faded. Yet, the white dwarf it leaves behind is a strange and permanent monument to this act of cosmic recycling. Left behind after the nebula's glow fades, the white dwarf is a stellar ghost. It contains the entire mass of a star like our Sun, crushed into a sphere no larger than Earth. A single teaspoon of its material would weigh many tons on our world. This incredible density defies our everyday experience. What holds it up from collapsing into an even smaller point? The answer lies not in fire, but in the bizarre rules of the quantum world. A force called electron degeneracy pressure provides the final, unyielding support. This is not a force born of heat or energy, but a fundamental law of physics that says electrons simply cannot be squeezed any closer together. It is the last line of defense against the star's own weight. With no nuclear fusion left to sustain it, the white dwarf embarks on its final journey. It is a dying ember, glowing white-hot from the tremendous heat trapped inside. Over billions upon billions of years, it will slowly radiate this heat away into the cold of space, cooling and reddening like a forgotten piece of coal in a cosmic fireplace. Its ultimate fate is to become a black dwarf, a cold, dark, and invisible crystal of carbon and oxygen, drifting forever through the galactic void. This is the quiet, peaceful end for the vast majority of stars. Yet for some, this quiet is an illusion. If a white dwarf has a nearby companion star, its immense gravity can begin to steal gas from its neighbor. This stolen material piles up on the white dwarf's surface, compressing and heating until it reaches a critical tipping point. The entire accumulated layer of hydrogen can then ignite in a runaway thermonuclear explosion. We see this from Earth as a nova, a sudden, temporary brightening of a star. In even more extreme cases, if too much mass is added, the white dwarf itself can be pushed past a stability limit, leading to a cataclysm that utterly destroys it. For most solitary stars, however, the white dwarf stage is the final, graceful exit. It is a monument to a life once lived, a dense cinder that slowly fades into the background hum of the universe, its atoms locked away for an almost eternal quiet. But this is only one possible ending to a star's story. What happens to the stars that are too massive to settle for this quiet fade, the true giants of the cosmos? While a white dwarf represents a star's quiet retirement, the universe's true giants meet a far more spectacular end. Stars born with more than 8 times the mass of our Sun live lives of extreme intensity, burning through their colossal fuel reserves in just a few million years. Their immense gravity forces their cores to become unimaginably hot and dense, turning them into furnaces of staggering power. This allows them to do what smaller stars cannot. They do not stop at fusing helium into carbon. They push onward, using the ash of one fusion process as the fuel for the next. A complex, layered structure builds up inside the star like the layers of a cosmic onion. At the center, silicon burns to create iron. Surrounding it are separate shells where oxygen burns to silicon, neon to oxygen, carbon to neon, and helium to carbon. Each layer is a testament to a different stage of nuclear fusion, a record of the star's furious race against its own gravity. In this frantic process, the star forges most of the elements that make up our world, from the oxygen we breathe to the calcium in our bones. It becomes a true cosmic alchemist, creating atoms that did not exist when the universe was born. But this creative fury contains a fatal flaw. The star's entire existence is built on a simple principle: fusion releases energy, and that energy pushes outward to hold the star up. The formation of iron in the core shatters this balance. Fusing iron atoms together does not release energy, it consumes it. In an instant, the star's central engine seizes. The outward pressure that has supported the colossal star for millions of years vanishes. With nothing left to fight the relentless pull of gravity, the core collapses catastrophically. In less than a single second, an iron core the size of Earth is crushed into a ball of neutrons barely the size of a city. This sudden, violent implosion triggers a shockwave of unimaginable force that ripples outward, blasting the entire star apart. The stage is set for the star's final, defiant act, a supernova explosion that will outshine an entire galaxy. The star's heart becomes an iron coffin. For millions of years, its core has been a furious engine of creation, forging ever heavier elements, but the formation of iron is a fatal turning point. Unlike every fusion reaction before it, forcing iron atoms together does not release energy, it violently steals it. The star's central support system vanishes in an instant. After a lifetime of brilliant defiance, gravity wins. The core, a sphere of iron as massive as 1.5 of our suns and as wide as Earth, has nothing left to hold it up. It implodes in less time than it takes to blink. This colossal object collapses inward at speeds approaching a quarter of the speed of light. The forces at work are beyond comprehension. The atomic structure of matter itself is obliterated. Protons and electrons are crushed together, merging to form neutrons and releasing a ghostly flood of particles called neutrinos. What was once a star's heart is now a sphere of pure neutrons, a city-sized object of unimaginable density. The collapse does not go quietly. The infalling outer layers of the star, plummeting at hypersonic speeds, slam into this rigid new surface. They rebound in a titanic shockwave, a cosmic sonic boom of incalculable power. This rebounding matter is then hit by the torrent of neutrinos racing out from the core, adding unimaginable pressure to the blast. The combined force rips the entire star apart from the inside out. This is a Type II supernova. For a few glorious weeks, this single dying star can outshine its entire host galaxy, radiating more energy than our Sun will over its entire 10 billion-year lifetime. In this apocalyptic fire, the true magic happens. The incredible heat and neutron flux in the expanding blast wave forge elements far heavier than iron. Gold, silver, uranium, the iodine in your body, the xenon in a car's headlight, all are created in this frantic, chaotic crucible. The supernova scatters these newly minted elements, along with all the others the star created during its life, across light years of space. This is the universe's most powerful act of recycling, seeding future generations of stars, planets, and life with the full periodic table. That brilliant flash, outshining entire galaxies, is the universe's most effective recycling plant in action. Within the heart of that expanding fireball, conditions become so extreme that they forge the heaviest ingredients of our world. This happens through a frantic process called rapid neutron capture, or the Are process. As a tsunami of neutrons floods outward from the collapsing core, atomic nuclei are bombarded. They grab these neutrons faster than they can naturally decay, building up atom by atom into incredibly heavy, unstable forms. These then settle down into the stable, precious elements we know. It is here, in this fleeting inferno, that gold is minted, silver is crystallized, and the uranium that powers our nuclear reactors is born. The very iodine essential for your thyroid gland, the platinum in a catalytic converter, all were created in this chaotic crucible. Then, the supernova's titanic shockwave takes over. Racing outward at thousands of kilometers per second, this blast front seizes the star's entire enriched contents, the oxygen and carbon from its earlier life, plus the newly forged gold and uranium, and hurls them violently into the void. This stellar shrapnel mixes with the tenuous gas and dust of the interstellar medium, seeding vast clouds with the full diversity of the periodic table. Every single heavy element on our planet, from the iron in your blood to the calcium in your bones, was created in a cataclysm like this. We are not just made of stardust, we are made of supernova dust, the remnants of the universe's most violent and creative explosions. As this enriched cloud drifts away, the story of the star's core, the trigger for this entire spectacle, is just beginning. When the supernova's fury subsides, the collapsed core remains. If this remnant weighs more than 1.4 times our Sun but less than 3, it does not become a quiet white dwarf. It becomes something far stranger, a neutron star. This is matter pushed to its absolute breaking point. Imagine crushing the entire mass of a star, a colossal sphere millions of kilometers wide, down into an object no larger than a city. The density is beyond human comprehension. A single sugar cube-sized piece of this material would weigh not just tons, but billions of tons on Earth. It is so dense that atoms cannot exist. Electrons are forced into protons, transforming everything into a solid, city-wide sea of neutrons, held apart only by a quantum force known as neutron degeneracy pressure. This is the final, desperate defense against the star's own weight, preventing it from collapsing into an infinite point. But this incredible density is only part of the story. The star's original spin is now concentrated into this tiny sphere, causing it to rotate at a dizzying speed. A star that once turned sedately over weeks can now spin hundreds of times every single second. Its magnetic field, already powerful in life, is compressed and amplified to become the strongest force field in the known universe, 1 trillion times stronger than Earth's. Some of these rapidly spinning neutron stars become cosmic lighthouses, known as pulsars. Their intense magnetic fields funnel radiation into narrow beams that shoot out from their magnetic poles. If these poles are misaligned with the star's rotation axis, the beams sweep across the sky with every spin. From our vantage point on Earth, we see a regular, repeating pulse of energy, a brilliant, rhythmic flash in the darkness. These precise cosmic clocks allow us to detect and study these otherwise invisible objects. The formation of a neutron star is not just a final act, it is an active player in the cosmic recycling process. Its intense gravity can shape the expanding cloud of the supernova remnant, and its fierce radiation can cook the surrounding gas, triggering new waves of chemical complexity. A neutron star is a monument to the most extreme physics the universe can muster, a direct and spectacular product of a giant star's death, proving that even in its final moments, a star can create something utterly new and astonishing. These cosmic lighthouses are called pulsars, and their precision defies belief. A pulsar is a rapidly spinning neutron star, its intense magnetic field funneling radiation into two narrow, opposing beams. If this cosmic lighthouse is misaligned, its beams sweep across the darkness with each rotation. When one of those beams flashes across our telescopes, we detect a pulse. The rhythm of these pulses is staggeringly exact, more reliable than any atomic clock we can build. The first pulsar discovered had a period of just over 1 second, a signal so regular that astronomers half-jokingly labeled it LGM for little green men, before the true, natural explanation was understood. This incredible rotational stability is not just a curiosity, it is a powerful scientific tool. By tracking the slightest deviations in the timing of these pulses, scientists can test the very fabric of spacetime. They have used pulsars to confirm the existence of gravitational waves, the ripples in spacetime predicted by Einstein, and to search for the subtle wobbles that might indicate planets orbiting these stellar corpses. Each precise tick is a heartbeat from a long-dead star, a steady drumbeat echoing the violence of its birth. But a pulsar is not merely a passive clock. It is an active, often violent, participant in its neighborhood. The same powerful magnetic fields that create the beams can also generate intense winds of charged particles, carving into nearby clouds of gas and influencing the formation of new stars. These spinning remnants are the universe's way of taking a cataclysm and turning it into both a precision instrument and a sculptor. Their rhythmic flashes a permanent signature of the supernova that gave them life. For the most massive stellar giants, even the neutron star's desperate defense fails. When the collapsing core crosses a threshold of roughly 3 solar masses, the pressure becomes too great for any known force in the universe to withstand. Neutron degeneracy pressure itself is overwhelmed. The collapse does not stop. It continues unchecked and unstoppable, crushing the core's matter into an infinitely dense point known as a singularity. This creates a region of space-time where gravity is so overpowering that the universe's ultimate speed limit, the velocity of light, is no longer fast enough to escape. We call this phenomenon a black hole. The point of no return is marked by an invisible boundary, the event horizon. Once any matter or energy crosses this threshold, it is lost forever from our observable universe, its information sealed inside an inscrutable gravitational prison. This seems like the absolute end of the line for cosmic recycling, a one-way trip into oblivion where matter is effectively erased. Yet, even in this ultimate act of consumption, black holes play a vital role in the galactic ecosystem. Their monstrous gravitational pull creates a violent and energetic environment around them. If a black hole has a companion star, it can strip gas from its neighbor, pulling the material into a vast, swirling disk of superheated plasma called an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to glow with intense X-rays before it makes its final, fatal plunge across the event horizon. These powerful emissions can be detected across the galaxy, acting as beacons that reveal the presence of an invisible monster. On a grander scale, the energy released from these feasting black holes can blow enormous bubbles of hot gas out into the wider galaxy, preventing vast clouds of cool gas from collapsing to form new stars. In this way, a supermassive black hole at a galaxy's heart can act as a cosmic regulator, putting a brake on star formation and controlling the pace of galactic evolution. The black hole, born from the death of the most massive stars, becomes a gravitational governor whose silent, dark presence shapes the future of everything around it. The brilliant flash of the supernova is only the beginning of the story. Long after the light fades, a colossal wave of destruction and creation continues to race outward. This is the supernova remnant, an expanding bubble of incandescent gas and cosmic debris that can stretch for dozens of light years. Inside structures like the magnificent Crab Nebula, the environment is one of beautiful chaos. The gas, heated to millions of degrees by the original blast, glows fiercely across the electromagnetic spectrum. Threaded through this cloud are immense filaments of dust, rich with the heavy elements forged in the star's death throes. At the heart of this maelstrom, the central neutron star often powers the entire display, its intense radiation and powerful winds acting like a cosmic egg beater, churning the cloud and lighting it up from within. This remnant is far more than a ghost. It is a dynamic and active engine. As the shell expands at thousands of kilometers per second, it plows into the quiet, cold gas of the interstellar medium. The shock front acts like a cosmic snowplow, gathering up this primordial material and compressing it into dense, cool sheets and filaments. Within these compressed regions, a remarkable transformation can begin. The gentle balance of the cloud is disrupted. Pockets of gas become so dense and heavy that their own gravity takes over, causing them to collapse. In these newly triggered stellar nurseries, the next generation of stars begins to flicker to life. A single star's death directly catalyzes the birth of hundreds more. This is the ultimate act of cosmic generosity. The supernova remnant ensures that the legacy of the dead star is not lost. The cloud becomes a perfect mixing bowl, where the newly minted gold, iodine, and uranium are thoroughly churned together with the more common hydrogen and helium swept up from space. The resulting blend is a far richer recipe for star formation. When this enriched material eventually collapses to form new stars and planets, those worlds will be built from a full palette of elements. They will be rocky worlds with iron cores, planets with atmospheres rich in nitrogen and oxygen, and worlds with the chemical complexity necessary for life to one day emerge. The supernova's tombstone becomes the galaxy's most fertile cradle. This enriched cloud of debris from supernova and planetary nebulae does not simply vanish into a void. It becomes part of a vast cosmic reservoir known as the Interstellar Medium. Think of the space between stars not as an absolute emptiness, but as an incredibly thin, dynamic fog. This fog is a mixture of gas, predominantly hydrogen and helium, and microscopic dust grains, all drifting through the immense distances. It is the universe's ultimate recycling bin, the repository for everything a star gives back. Every gust of stellar wind, every glowing shell of a planetary nebula, and every cataclysmic supernova blast dumps its processed material right here. The interstellar medium is both the raw material for new stars and the final resting place for the ashes of the old. It exists in a constant state of flux, with pockets that are incredibly hot and diffuse right next to regions that are frigid and dense. This churning is driven by the very stellar lives it spawns. Newly born massive stars flood their surroundings with intense radiation, heating the gas and carving out vast bubbles, while the shockwaves from dying stars compress cold clouds into new stellar nurseries. This continuous exchange is the engine of galactic evolution. With every stellar generation, the interstellar medium becomes slightly richer, its concentration of heavy elements, what astronomers call metallicity, slowly increasing. The oxygen you breathe, the iron in your blood, and the silicon in the ground beneath your feet were all once floating in this cosmic reservoir, patiently waiting for their turn to become part of a new star, a new planet, and ultimately you. One of the most profound truths in the cosmos is that death gives birth to new life. The shockwave from a supernova is the universe's great sculptor, traveling for millennia through the silent darkness of the interstellar medium. When this titanic wall of energy finally slams into a quiet, cold cloud of gas and dust, it does not simply pass through, it squeezes. The immense pressure of the shock front overpowers the cloud's own feeble internal forces, pushing countless particles closer together. In that moment of extreme compression, gravity finds its opening. What was once a stable, drifting cloud suddenly becomes a collection of dense, collapsing knots. Each knot is a potential star, its long sleep interrupted by the violence of a death that occurred light years away. This is how a stellar catastrophe becomes a stellar nursery. The evidence for this is written in the very rocks of our solar system. Ancient meteorites, the pristine leftovers from the formation of our planetary system, contain a telltale signature. Trapped within their crystal structures are the decay products of short-lived radioactive isotopes, like aluminum-26. These unstable elements could not have survived the long, quiet eons before the sun was born. Their presence is a radioactive clock ticking down to a specific moment of injection. They are the smoking gun, proving that a nearby supernova exploded, seeding the cloud that would become our solar system with its freshly forged atoms, and likely providing the very shockwave that triggered its collapse. The death of a massive star did not just supply the iron for Earth's core and the calcium for our bones. It may have also given the initial, essential nudge that started the entire process, setting in motion the chain of events that led to a stable star, a circling Earth, and eventually to us. Stellar death is not a final conclusion but a cosmic catalyst, a necessary end that guarantees a new beginning. But the cosmos rarely works in isolation. Many stars are not born alone, but in pairs or groups, dancing through their lives in a gravitational embrace. These binary systems introduce a dramatic new chapter to the story of cosmic recycling, where the death of one star can trigger a spectacular second act for its partner. Imagine a stellar partnership where one star, having lived its life, has settled into a quiet retirement as a dense white dwarf. Its companion, however, might still be a vibrant, hydrogen-rich star. The white dwarf's immense gravity begins to act as a cosmic thief, slowly siphoning a stream of hydrogen gas from its living neighbor. This stolen material doesn't just vanish. It spirals down, piling up in a thin, incredibly hot layer on the white dwarf's surface. For a time, this process seems stable, but with every passing second, the layer grows denser and hotter, a ticking time bomb of potential energy. Eventually, it crosses a critical threshold. The entire accumulated shell of hydrogen ignites at once in a runaway thermonuclear firestorm. This is a nova, a brilliant flash that can make a faint star visible to the naked eye for a few glorious nights. But sometimes the theft is too successful. If the white dwarf pulls in so much mass that it is pushed past a specific stability limit, the result is not a surface explosion, but a complete demolition of the star itself. This is a Type 1, a supernova, a cataclysm of such precise and predictable brightness that astronomers use them as standard candles to measure the vast distances of the universe. Crucially, the sheer violence of this explosion is what forges the majority of the universe's iron. Every car frame, every steel skyscraper, and the very iron core of our planet was born from a stellar partnership that ended in a violent theft and a titanic detonation. Yet the drama does not end there. If a binary system contains two neutron stars, the ultimate dance of the dead begins. These city-sized remnants of supernova spiral inward over eons, their orbits decaying as they radiate energy in the form of gravitational waves, ripples in the fabric of space-time itself. When they finally merge, the collision unleashes an inferno of neutrons. In this fleeting, golden moment, the rapid neutron capture process runs wild, forging a treasure trove of the heaviest elements. A significant portion of all the gold in the universe, from wedding rings to the reserves in bank vaults, along with platinum and other precious metals, is created not in the heart of a supernova, but in the violent merger of two neutron stars. These dynamic interactions prove that the universe's recycling program is not a lonely, solitary process. It is a complex, often violent, and deeply interconnected dance where the fate of one star is forever tied to the actions of another, seeding the galaxy with the elements for new worlds through partnership, theft, and collision. The universe's grandest recycling program relies on its smallest workers. Floating within the vast clouds between stars are countless microscopic specks, cosmic dust grains forged in the hearts of dying suns. When a red giant star nears the end of its life, its churning, cooling atmosphere becomes a factory for these particles, atoms of silicon and carbon created in the star's own nuclear furnace, linked together to form tiny solid seeds. Then powerful stellar winds, flowing out from the dying star like a cosmic exhale, blow these newly formed grains into the depths of interstellar space. Supernova explosions contribute their own share, ejecting a blizzard of even more complex dust. This is not mere dirt, it is the fundamental grit from which new worlds are assembled. These minute grains serve a purpose far greater than their size suggests. In the cold, dark molecular clouds where new stars are born, they act as tiny meeting halls. Individual atoms like hydrogen and oxygen drift far too quickly to ever link up on their own. But when they stick to the solid surface of a dust grain, they can linger, meet other atoms, and react. It is on these microscopic platforms that simple water molecules can first assemble. Even complex organic compounds, the carbon-based precursors to life, can form on these tiny, frozen platforms in the void. Without this dust, space would be a far emptier and more sterile place, a universe of lonely atoms unable to form the molecules that are the next step toward complexity. These dust grains are also cosmic sunshades. Dense molecular clouds are nurseries, but they would be torn apart by the harsh ultraviolet radiation from nearby young, hot stars. The dust suspended within these clouds absorbs this destructive energy, shielding the fragile hydrogen molecules inside. This protection allows the cloud to cool down. As it cools, the internal pressure drops and gravity can finally get a firm grip, initiating the slow collapse that leads to the birth of a new star and its surrounding planetary disk. Later, within that spinning disk, the dust performs its final and most tangible act. The grains begin to stick together, colliding gently to form pebbles, then rocks, then planetesimals. Every mountain on Earth, every asteroid in the belt, and every icy comet in the outer solar system began as these microscopic fragments of long-dead stars. The iron in the ground beneath you and the silicon in the sand on a beach were once part of this incredible, invisible dust, completing a cycle that turns the ashes of old stars into the bedrock of new worlds. The story of the elements is a tale of two very different forges. For all the atoms up to iron, a star's life is a story of fusion, of building blocks by forcing smaller ones together. But to create anything heavier, to move beyond iron on the periodic table, the universe requires a more extreme and violent strategy. It needs a flood of free neutrons, and how those neutrons are delivered determines the entire character of the element being forged. The first method is a patient, almost gentle alchemy known as the slow neutron capture process, or the S process. This occurs deep within the stable, churning interiors of red giant stars. Here, atomic nuclei like iron float in a sea of free neutrons, capturing them one at a time over thousands of years. After each capture, the nucleus has time to stabilize, sometimes spitting out a particle to settle into a slightly heavier, stable form. It is a slow, methodical climb up the periodic table, creating about half of the elements heavier than iron. The barium used in medical imaging, the strontium that gives fireworks their brilliant red color, and the technetium found in the spectra of these very stars were all built this way, atom by patient atom, inside aging suns. But this careful process has its limits. It cannot create the very heaviest, most exotic elements. For gold, platinum, and uranium, the universe needs chaos. It needs the rapid neutron capture process, the R process. Here, in the furious heart of a supernova shockwave or the unimaginable density of colliding neutron stars, a tsunami of neutrons strikes atomic nuclei. They are bombarded, capturing dozens of neutrons in a fraction of a second, far faster than they can naturally decay. This creates wildly unstable, bloated nuclei that then settle down through radioactive decay into the stable, precious metals we know. This is why the gold in a wedding ring or the uranium in a power plant is so rare. Their birth requires the most catastrophic events in the cosmos. Every single heavy element on Earth, from the patient S-process products to the violent R-process treasures, carries the indelible signature of a star's death. The complete diversity of the periodic table is therefore a direct and beautiful consequence of this endless cosmic cycle of creation and destruction. This cycle of stellar life and death is the very heartbeat of our galaxy. Our Milky Way is not a static collection of stars but a giant, dynamic ecosystem, a cosmic metropolis where matter is in constant motion. The interstellar medium is its lifeblood, a vast reservoir of gas flowing through the spiral arms. Within this reservoir, stars are born from the densest clouds. They live out their lives, and when they die, they return their enriched ashes back into the galactic pool. This is a continuous loop of creation and return, a grand galactic metabolism that has been running for over 13 billion years. The galaxy itself orchestrates this flow. The immense rotation of the Milky Way's spiral arms churns the interstellar medium, while the powerful shockwaves from supernova act as immense pumps. These explosions can blow gigantic bubbles in the gas, driving enriched material high above the galactic disk or compressing nearby clouds to trigger the next wave of star birth. This circulation is not random. It creates a gradual, cosmic enrichment gradient. The galactic center, where stars have lived and died in countless generations, is rich with heavy elements. The outer reaches are more pristine, dominated by the primordial hydrogen and helium from the dawn of time. As the galaxy ages, this metallicity slowly increases, ensuring that each new generation of stars and planets is built from a slightly more complex set of ingredients than the last. This stellar life cycle directly dictates the evolution and appearance of the galaxy itself. A young galaxy is gas-rich and blue, blazing with the light of short-lived massive stars. But as eons pass and its gas reservoir is steadily locked away in long-lived stars, white dwarfs and neutron stars, its star formation rate slows. The brilliant blue giants die out, leaving behind the cooler, longer-lasting red stars. The galaxy's color shifts from a vibrant blue to a softer yellow, and finally to a muted red. The relentless recycling of stars, therefore, is not just a process within the galaxy. It is the process that built the galaxy, shaping its structure, controlling its light, and writing its entire history across cosmic time. The death of a single star, then, is a single note in a galactic symphony that has been playing for billions of years, its echo shaping the destiny of everything that follows. Our own sun holds a personal map of this entire cosmic journey. Its future is not a mystery, but a destiny written by the same laws that govern every star we have witnessed. In about 5 billion years, the sun will face its own midlife crisis. The hydrogen fuel in its core will finally run dry, ending its long, stable main sequence life. Its core, a growing ball of helium ash, will begin to collapse under its relentless gravity. The resulting surge of heat will ignite a shell of hydrogen around the core, burning with a ferocious new intensity. This will unleash a wave of energy so powerful it will push the sun's outer layers outward, forcing it to swell to a monstrous size. It will become a red giant, its bloated atmosphere stretching across the sky. In this final, fiery act, the inner solar system will be remade. Mercury and Venus will almost certainly be engulfed and vaporized. Earth will be scorched, its oceans boiled away and its crust melted to slag, becoming utterly uninhabitable long before the sun's outer edge might even reach its orbit. Yet within this apparent destruction, the sun begins its most crucial work. In its red giant heart, the triple alpha process will ignite, forging the star's internal helium into carbon and oxygen. It is the first and only time our star will create these fundamental building blocks of life. After a relatively brief period of instability, the sun will gently shrug off its entire outer atmosphere. This expelled shell of gas, now rich with newly minted carbon and oxygen, will expand into space, illuminated by the intense ultraviolet light from the exposed core. From a distant world, any alien astronomers would see a beautiful, glowing planetary nebula where our solar system once was, a final, artistic flourish lasting tens of thousands of years. At the center of this glowing cloud, the sun's core will be laid bare, no longer supporting fusion. This incredibly dense ball of carbon and oxygen will be crushed by gravity into an object no larger than Earth. This is our sun's ultimate fate, to become a white dwarf. Initially blazing with searing heat, this stellar ember will have no energy source left. It will slowly, over trillions upon trillions of years, radiate its remaining heat into the void, cooling and fading from white to yellow to red, and eventually to a cold black dwarf. But the story does not end with this cooling cinder. The beautiful nebula, the sun's gift to the galaxy, will continue its journey. That cloud of gas, carrying atoms that were once part of Earth and even our own bodies, will drift and mix with the wider interstellar medium. Over countless millions of years, this enriched material will be drawn into a vast, cold molecular cloud. Gravity will once again work its magic, causing a pocket within that cloud to collapse. In that new stellar nursery, a new star will one day ignite. Around it, a disk of dust and gas will coalesce, and from that disk, new planets will form. Those rocky worlds will be built, in part, from the carbon, oxygen, and other elements our sun forged in its death throes. The iron from a forgotten bridge on Earth, the calcium from a long-vanished sea creature, the very atoms that once made you, could one day be incorporated into the mountains, oceans, or even the biology of a new world orbiting a new sun. Our solar system story is a single, perfect verse in the galaxy's endless poem of renewal. Our very presence here is a direct product of this cosmic recycling. The Anthropic Principle offers a startling perspective on this fact, proposing that the universe we observe must be compatible with the conscious life that observes it. Its physical laws and constants appear to be perfectly balanced on a razor's edge. A tiny alteration in the strength of the nuclear force, for instance, would have had catastrophic consequences for our existence. The fundamental element of life, carbon, is forged inside stars through a precise and delicate nuclear reaction. If the forces binding atomic nuclei were even slightly weaker, 3 helium nuclei could never come together to form a stable carbon atom. If those forces were slightly stronger, the carbon would rapidly fuse into other elements and vanish. We would live in a carbonless cosmos, a universe without the backbone of organic chemistry, without planets and without us. This fine-tuning extends to the grand cycle of stellar death itself. If the most massive stars did not explode as supernova, they would simply collapse into black holes, locking away their newly forged heavy elements forever. The universe would be a sterile sea of hydrogen and helium, with no material for rocky planets, no oxygen for water, and no iron for planetary cores. Our ability to breathe, to walk on solid ground, and to think about these very ideas hinges on a long chain of stellar cataclysms that unfolded over billions of years. We are not accidental tourists in a random cosmos. We are the universe becoming aware of itself, a fleeting thought made possible by the carefully orchestrated death and rebirth of stars. This realization reframes our entire quest for knowledge. When we peer through a telescope, we are not just looking out at a distant external reality. We are looking back at our own origins. The light from a supernova remnant is not just a message from a dead star. It is a chapter in our own autobiography, written in the language of nuclear physics. Our curiosity about the cosmos is, in a very real sense, the cosmos wondering about itself. We are a temporary, conscious expression of the universe's endless and ancient cycle of renewal. This cosmic legacy is written in the very stars we search for planets around. Our quest to find another Earth is guided by the ancient cycle of stellar death and rebirth. We now know that planets are not rare accidents, but a common byproduct of star formation. Yet, not all stars are equally likely to host rocky, Earth-like worlds. The key lies in a star's metallicity, a term astronomers use for the abundance of elements heavier than helium within it. Think of metallicity as a cosmic ingredient list. A star born recently from an interstellar cloud enriched by countless supernova and planetary nebulae will have a high metallicity. Its protoplanetary disk will be rich with iron, silicon, oxygen, and carbon, the essential raw materials for building terrestrial planets. Our own Sun is one such star, a metal-rich descendant of stellar ancestors that lived and died long before it was born. In contrast, the very first stars in the universe were composed almost entirely of hydrogen and helium. They lived fast, died in colossal supernova, and seeded the void with the first heavy elements. Any planets forming around those early stars would have been gas giants or barren worlds without a rocky crust. When our telescopes today identify a distant star, one of the first things we can measure is its metallicity. This single piece of data acts as a powerful filter. A star with high metallicity immediately becomes a prime candidate in the search for rocky exoplanets. It tells us that this star system was built from recycled stardust that had already been processed through the cosmic forge, material that contains the full palette of elements needed for a planet like our own. This understanding transforms our search from a blind scan of the sky to a targeted investigation. We are not just looking for any planet. We are looking for the children of stars, worlds born from the same enriched ashes that made our own existence possible. Every rocky exoplanet we confirm is a testament to this grand cycle, a direct descendant of the elemental gifts from long-dead suns. This grand cycle of stellar life and death is the engine of a vibrant cosmic era, but it is an era with an expiration date. The universe's fuel supply is finite. The pristine hydrogen and helium gas that fills the interstellar medium, the essential raw material for building new stars, is gradually being consumed. With every generation of stars that ignites, the total reservoir shrinks. Over trillions of years, this will cause the rate of star formation to slow from a roaring fire to a faint, sputtering flicker. The brilliant blue giants, those short-lived titans that die in supernova, will be the first to vanish from the cosmic stage. The universe's demographics will shift dramatically. The night sky of the far future will be dominated by the old and the faint, by the countless red dwarfs that burn their fuel with such miserly efficiency they can shine for trillions of years. These faint, cool stars will be the last beacons in an increasingly darkening cosmos, outliving all their more massive siblings. Eventually, one by one, even these final stars will exhaust their fuel. Their nuclear fires will gutter and die. What remains is a cosmic graveyard, a universe populated by the stellar corpses we have already met, the white dwarfs, neutron stars, and black holes drifting in an ever colder void. The planets that orbit them will be frozen, airless worlds, their surfaces locked in perpetual deep freeze. The vibrant, dynamic recycling of elements that defined our universe's most creative chapter will grind to a halt. The great forges will fall silent, yet the legacy of that cycle is not lost. All the complex atoms forged in the hearts of countless stars, the carbon and oxygen, the gold and uranium, do not simply disappear. They remain locked away for eons within the crystalline structures of cold white dwarfs, the ultra-dense matter of neutron stars, and the frozen rocks of dead planets. They are the permanent record of a spectacularly creative age. While the universe will continue to exist for timescales that dwarf its current age, its most active and luminous phase, the era of stellar life and rebirth, is a finite window. We are living in the bright, bustling morning of cosmic history, a golden age of transformation where stardust is continually reshaped into new suns, new worlds, and the potential for life. This makes our existence and our ability to witness this grand cycle not just a fortunate accident, but a precious glimpse into the universe's most prolific and defining epoch. This grand cosmic cycle, from nebula cradle to stellar grave, is our own origin story written in the language of physics. We have journeyed from the silent collapse of gas clouds to the brilliant flash of fusion, from the gentle expulsion of planetary nebulae to the cataclysmic violence of supernova. At every turn, we have witnessed the universe operating as the most efficient recycling plant imaginable, where nothing is wasted and the end of one story is the raw material for the next. The death of a star is not a final curtain call, but a necessary dispersal, scattering enriched ashes that will one day coalesce into new suns, new planets, and perhaps new life. This truth connects every one of us to the cosmos in the most intimate way possible. The iron that carries oxygen through your bloodstream was forged in the final moments of a massive star's life. The calcium that strengthens your bones was created in the heart of a red giant. Every breath you take fills your lungs with oxygen that was once a building block inside a star that died billions of years ago. The astronomer Carl Sagan captured this perfectly when he said, "We are made of star stuff." This is more than a beautiful poetic idea, it is a chemical and physical reality. Understanding this cycle should fill us with a profound sense of wonder. We are not just living on a planet, we are living on a collection of cosmic artifacts, a museum built from the remnants of ancient suns. This knowledge also comes with a deep responsibility. We are the universe become conscious, a way for the cosmos to understand itself. The same elements that fuel the stars now fuel our thoughts. This places upon us a duty to care for this fragile world made of stardust, to protect the delicate conditions that allow this conscious chapter of the universe's story to continue. If this journey through the life and death of stars has reshaped how you see your place in the cosmos, we would love to hear your reflections in the comments below. For more explorations into the profound mysteries of space, be sure to subscribe.